Okay. Now I want to see if this works. Okay, so let's see if this works. Do I have a microphone? So what do I need to do here? Okay. Videos. Oh. Okay. BK11 Kent. Aha. Okay, good. So that's a starting point. Just something fell down. Okay, so let me see. Okay, good. Ha! I think sound is working. And now I try. Aha, okay. So, are we back in business? I need to see if we are going back into business here. Ah, okay. Good. It looks like it is working. Right. So, most wonderful good afternoon, everybody. Can you, by any chance, hear me? And how's the sound quality? Yes, yes, you can hear me. And you even can see me. Hey, how cool is that, huh? Although I think you probably don't want to see me. And I take these headphones out. So now you have to tell me if the sound breaks up. Okay? Everybody happy? How has this week been for you guys? Good? Luke says good week. I'm very pleased to hear that. I have seen there is quite an interesting discussion on the group chat going on about the potential strike action. And I think that's quite an interesting discussion. And so far, I have to say my week has been reasonably okay. Of course, in a way, I miss you, all of you. And I'm thinking about next week. Probably I should see you again. So maybe we do a face-to-face session, unless people say to me they really want to have this new format more often. So I might even send out a poll or something like that. Right, now I'm not entirely sure how many people I've got here. And if I look to the side, this is not just because I'm ignoring you, it's just simply the setup of my, my broadcasting studio here, where I check the comments on the big screen. So what I want to do with you today is I want to tell you a little bit more about kinetics and how kinetics actually leads to some really cool stuff that is actually the essence of life. So let's see if I can change the picture here. Right. Now, we said in previous sessions that we were talking, when we talk about kinetics, we talk about rates. And especially when we have, for example, a reaction A is converted to B. And we said, let's look at the rate of A. And we said in a case like that, we can say rate A equals minus K times A to the power of M. And we said that is our rate order. And that here is our rate constant. And we use the minus because A is consumed. Now, quite frequently what you will find is that instead of rate A and rate B and things like that, what people usually then use is not writing rate A. They just simply write a mathematical version of rate A and rate B and so on. And this basically is, we look at a change in the concentration of A. And this little d indicates a change, a very small change in A during a very small time period. So you very often see dA over dt. And this is nothing else. It means rate from the perspective of A. Rate from A's view. Okay, so I will usually in future use this writing, and then obviously it means dA over dt can be written as minus K times A to the power of M. And M, we said, can be basically anything, whatever is necessary in order to describe the rate independence of this substrate concentration. And likewise we can write in a case like that dB over dt equals, now we have the production of B, and therefore what is the sign? Absolutely right. Doesn't cause any problems. It must be positive, and we have plus K times. And of course, our rate for B is the same as the rate for A, just with a different sign. So we have times A to the power of M again. And we discussed the reasons for that the last time. So now that's how we can write these things. Okay, so let's see how we can look at it actually. And we can say if we, for example, have this reaction A is converted into B, we can plot these data. So if we plot, for example, the concentration of A here, and we look at the rate here, what we would see is, for example, if we have m equals 1, we have the reaction rate, dA, so dA over dt equals minus k times a to the power of 1. And this actually gives us the equation for a straight line. We have here mx plus, well, c, but we don't have a c here, so we can ignore that. So in our case, the graphic interpretation of this equation would be a straight, oops, that happens sometimes, I apologize. This would be our graph here with the gradient. What's the gradient? What is our gradient in this K? 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 Well, yes, it is K, or we could even say it is negative K, because the graph goes basically down here. So that would be the graph for dA over dt. What do you think would be the graph for dB over dt? What would be the graph for dB over dt? Yeah? Up or down? It's the positive gradient. Exactly. Yeah? It's exactly the opposite. It's almost like mirror image, like that. So that would be dB over dt. Absolutely right. Yeah, well done. It goes up. A reflection of the graph, Alana says, and that's exactly spot on. Now, very often we see things like that where we have rate so rate versus, oh, actually a substrate concentration. Have you seen something like that? Okay, Daniela says yes. When? Where? How? When did you see that? In enzymes, yeah. Lauren says enzymes. BI308, exactly. That's the module that you're currently doing. Exactly. Now what you see here, yep, that's the lecture. Although I think he's called CAD, not CLAD. What you see here is something very, very interesting when you look at enzymes. Because when you look at Michaelis-Menten enzyme, you see something like that. Does that look vaguely familiar? Absolutely right. Now let's look at what's happening here, because that is something really, really fascinating. Now here we could say at a very low region here, And Kyle is right, it is a rectangular hyperbole. What we see here in this lower range of the substrate, very low substrate concentration, what we see here is that the rate equals S to the power of, well, it almost looks like a straight line. So it's probably powered to the power of S. And we have a rate constant. Now, obviously, I've done it slightly wrong because we are looking usually at the disappearance of S. But if we just simply say instead of rate, we look at the speed, then we don't need to worry about the negative thing. And we can draw it like that. So in this case, we look at a rate depends on the speed. Let me write that speed. Depends on the substrate concentration, right? At very low substrate concentration. What happens here when we are in this range here? Is the rate or the speed still dependent on the substrate concentration when we are in this high range of substrate? What do you think? Rihanna says nope. No? You're absolutely right. At very high substrate concentration, so very high S, what we find is that the rate or the speed no longer depends on S. Depends on S. How could we write that? We can write here rate equals K times S to the power of. And now, here is the big question. What would be the power of S? What do you think? Hey guys, you're good. You say S to the power of 0. Because anything to the power of 0 is what? Anything to the power of 0 is 1. Exactly. Absolutely right. So when we have high S, our rate equals K times 1. Our rate, in other words, is rate equals constant. The rate does not react to S, to the substrate concentration. It just simply stays constant. And actually, this is something really, really weird. What's going on with with enzymes, when we look at enzymes. So when we look at enzymes, in enzymes, and in particular in Michaelis-Menten enzymes, the rate or speed versus versus S is changing, or the rate order M shifts from 1, rate order of 1, at S very low to 0 order when S is very high. And actually, one can even write that mathematically for an enzyme reaction, because M, the order of our enzyme reaction, is actually given by the equation S divided by Km plus S. And Km is the Michaelis concentrate, is the Michaelis-Menten constant. Have you seen that before? S over Km plus S. Have you seen that? Again, it's in the Michaelis-Menten equation. So in this case, our M is not a constant throughout, but M actually depends on the substrate concentration. And in a way, what you can see is that if, for example, S is very, very small, then the big thing is Km, and you've got something small divided by something big, and that approaches 0. Or if S is very, very big, then Km doesn't play any role, and the two S's cancel each other out, and you have M equals 1. So for S very high, you have 0, and for S very low, you have 1. Okay, but before we go into further detail with these weird and wonderful things, let me make it a little bit more interesting.